opinion.
In this video, we will talk about the rate law or the expression rate, as well as how to solve for the rate constant K. The rate law gives a description of how the reaction changes when the concentration of a specific reactant changes. Now this is the general rate expression of the rate law. We have the rate of the reaction equals to the rate constant multiplied by the concentration of A to the power of X multiplied by the concentration of B to the power of Y. These brackets indicate concentration, while X and Y is the order of the reaction. Now you can use, instead of X and Y, you can use M or N or A or B. It's completely up to you. I went ahead and wrote down what each of the components of the rate law signify. So the rate tells you how fast a reaction proceeds and the change in concentration of reactants or products over time. K is a proportionality constant between the reaction rate and concentration of reactants. However, it doesn't depend on the concentration of reactants. K usually depends on the temperature as well as whether or not there is a catalyst present during the reaction. Now this X over here indicates that the reaction is in the X order of A. So A has order of reaction of X. And the same can be said for B. So B has a reaction order of Y. And in order to solve the overall order of the reaction, you would have to add X and Y together. Now here's something very important. The order of the reaction is not related to the stoichiometric coefficient. So for instance, we have the reaction right here. And as you can see, in front of chlorine dioxide, there's 2. This coefficient is not the order of the reaction. This is simply the coefficient to indicate how many molecules of chlorine dioxide you have in the equation. So, after calculated, the order of the reaction is 1. So, it is not related to the coefficient at all. You need to calculate the order of the reaction, and that data is mostly obtained from experimentation. Now before we get into the practice question, I would simply just like to talk about the differences between the reaction rate and the rate constant, as well as some important details that you will need to use for the practice questions. So the reaction rate, as previously stated, is the speed, the E is quite crooked, speed at which reactants are converted into products. It depends on the concentration of the reactants and can change over time as the reaction proceeds. Because over time, for instance, we have A turns into B, right? The concentration of A during the reaction will decrease. And at the same time, this results in an increase in the concentration of B. The rate constant, on the other hand, is a proportionality constant in the rate expression or rate law, and it relates the reaction rate to the concentrations of the reactants. Unlike the reaction rate, this is independent of the reactant concentrations, and instead it depends on the temperature and the presence of a catalyst. So let's say a reaction is fixed at a certain temperature. That will mean that the rate constant would remain constant. It will remain the same. However, if the temperature were to change, the rate constant would also change. And that would then apply as well to the presence, whether or not there is a catalyst during the reaction. As you can see on the left here, I wrote down some units. So the reaction rate has a unit of molars per second. However, the rate constant, the units depend on the order of the reaction. If it's the 0th order, it would be molars per second. If it's the first order, it will be 1 per second, or the rate constant per second. And if it's a second order, it will be the rate constant per molars times second. So just remember that the units change for the rate constant. So now let's determine the rate law and calculate the rate constant K for the following reaction from the following experimental data. The first step is to find or to establish the rate law. So that would simply be the reaction rate equals to K multiplied by the first reactant, that is S2O8 or peroxy disulfate. And we do not know the rate of reaction, so we would just put X there. You can also put M or N, whatever you like. The second reaction would be iodide. And the rate of reaction, I would just symbolize it with Y. So now we need to find X and Y. We need to determine how the reaction rate changes when the concentration of one reactant changes while the other is kept constant. So let's look at the experiments. I already went ahead and highlighted the concentrations of the reactants that are identical. So for experiment 1 and experiment 2, the concentration of S2O8 is the same. It's 0.08, right? And the concentration of iodide is 0.034 and 0.017. So when we plug it into the equation, these terms will cancel out. That will then leave an equation that only involves the iodide. And then we can solve for Y, and vice versa. If we use the data from experiments 2 and 3, where the concentration of iodide is the same, this would then leave us, these terms will cancel out, leaving us with S2O8, and then we can go ahead and solve for X. So I'll first solve for Y. So the first step is to find which experiments do we need to use. We need to solve for Y, meaning that we need to cancel out S2O8. So the concentration for SO8 has to be the same. So we need to use experiments 2 and experiments 1. Rate 1, this is the initial rate, divided by the initial rate 2. We just put the bigger number in the numerator. So that would then equal to the rate constant. Now the concentration of S2O8 in experiment 1 is 0.08 X, and the concentration of iodide in experiment 1 would be 0.034 within Y. And this stays the same, as you can see right here in experiment 2. And then the concentration of iodide in experiment 2 would be 0.017. Now here comes the fun part, is to cancel out the terms. So K cancel out, concentrations or the term of S2O8 cancels out. And this then leaves us with, and let us just simplify that. That would then just be 2 equals to 2 to the power of Y. And now all we need to do is to solve for Y. To do that, we need to take the natural logarithm on both sides. That would then be ln2 equals to Y multiplied by ln2. Then we need to divide the equation by this one, by this term, in order to isolate the Y or solve for Y. And Y would be ln2 divided by ln2. That would then give us with an answer of 1. So Y is 1. So the order of the reaction in terms of iodide is 1. Now the next step is to solve for X. We just do the same thing, but we need to cancel out the iodide term right here. So the concentration for iodide needs to be the same so that they can cancel out. So let us use experiments 2 and 3 because the concentrations of iodide are the same for both experiments. So the bigger term, I'm just going to write rate here, so that's shorter. Rate 3, rate 2. Now just cancel it out. K cancels out, 0.017 cancel out. Just simplify that, so this would also be 2 equals to 2 to the power of x. We need to take the natural log on both sides and solve for x, and we will get an answer of 1. Once the rate law has been determined, you can calculate the rate constant K by plugging in the reaction rate and the reactant concentrations from any experiment. So you can choose data from experiment 1, experiment 2, or experiment 3. It's completely up to you. Nonetheless, the answer should come out the same. So let's just solve for K. I'll choose experiment 1. So let's just plug all of the values into this equation. So the rate would be 2.2 times 10 to the power of negative 4 equals to K is what we're searching for. K times the concentration of S2O8 is 0.08 and X is 1 as we solved. The concentration of iodide is 0.034. So K would be 2.2 times 10 to the power of negative 4 divided by 0.08 times 0.034, and that would then give us a rate constant of 0.08. Now you may be wondering, what is a unit? Remember, before I said that the rate constant, the unit of the rate constant depends on the overall order of the reaction. In order to obtain the order of the reaction, we just need to add all of the orders together. So it would be overall order would be x plus y. X is 1, y is 1. So 1 plus 1 is 2. So the overall order of the reaction is 2. This is the unit, 1 or 0.08 per molars times a second.